This segment we're going to talk about the diesel cycle, and the diesel cycle is used to model a compression ignition engine or a diesel engine. So let's look at the four processes for a diesel engine. So during the intake stroke, the piston head moves down, the intake valve opens, and only air enters the chamber, as opposed to a gasoline engine where air and fuel enter. Then the piston head moves up to top dead center, compressing the air to a very high temperature and pressure. And at top dead center, a fuel injector injects fuel into the chamber. And because that air is at a very high temperature, that fuel spontaneously combusts or auto-ignites, and it forces the piston head down. Then the piston head moves back up and expels all the products of combustion. Once again, just like that Otto cycle, or like the spark ignition engine, it's not a true thermodynamic cycle. It's a mechanical cycle, because with each cycle you have fresh air coming in. It's not the same air during the intakes during that first process every single time. It's different air every single time, but we can model it like a thermodynamic cycle, and that allows us to get some rough estimate of some parameters that we'll be interested in calculating. Now, one important thing to notice, that in a compression ignition engine, there's no spark that initiates the combustion. And that's because with the diesel engine, we compress that diesel fuel to the auto ignition temperature of that diesel. So if we had a jar of diesel and it's sitting there at 25 degrees Celsius, then it doesn't do anything. And even if we threw a match in it, the match would just go out. Nothing would happen. If we heated it up to about 52 degrees Celsius, still nothing would happen if it was sitting there. But if we happened to take a match and tried to light it, it would light, because this is 52 degrees Celsius is about where the flash point of diesel fuel is. But if it just sat there and we didn't have any initiating factor for combustion, it would just sit there. Now, if we continue to heat it up to around 210, 260 degrees Celsius, this is around where the auto ignition temperature of diesel fuel is, and it would just all of a sudden spontaneously ignite, or auto ignite, or spontaneously combust. So that's the idea behind a diesel engine. You compress the air so it's at such a high temperature, so that when you inject the fuel into that high temperature environment, it automatically combusts. All right, so let's go through the four processes of an ideal diesel cycle, which is the thermodynamic cycle that we're going to use to model this particular cycle, to model the mechanical cycle, not the thermodynamic cycle. So this is an ideal diesel cycle. It's a thermodynamic cycle. So we've got air. That's we're going to make air standard assumptions. So we're working with air. We're treating this thing like air, and it's in a piston cylinder. And you'll see that it looks very, very similar to the Otto cycle. So 3 out of the 4 processes are the exact same as an Otto cycle. So from 1 to 2, you've got an isentropic compression. That's the same. From 2 to 3, you've got a constant pressure heat addition process. That's different. Then from 3 to 4, you've got an isentropic expansion. And 4 to 1, you've got a constant volume heat rejection process. So you see that the only thing that was different was that constant pressure heat addition process. The only thing that's different is the way that we model that combustion process. And we'll talk about that in just a little bit. In an Otto cycle, the power stroke was just during that expansion, that isentropic expansion process. However, with a diesel cycle, that power stroke goes from 2 to 4, because you're expanding during the isentropic expansion, obviously, but with the constant pressure heat addition process, if you've got air in a piston cylinder and you heat it up and the pressure is just remaining constant, it's going to be allowed to expand. So you have expansion from 2 to 3 and expansion from 3 to 4. So you've got a work output during both of those particular processes. So if we did the exact same thing that we did with the Otto cycle, we look at the 4 processes and we say, okay, well, what are the things in our toolbox that will allow us to analyze each of those processes? You would see that, not surprisingly, since 3 out of the 4 processes are exactly the same, so from 1 to 2, 2 to 3 is different, so we're going to come back to that, but from 1 to 2, 3 to 4, 4 to 1, all of those are exactly the same tools. that we used for the Otto cycle. So the first law boils down to the same equation, the ideal gas law, of course, that's the same. The isentropic relationships, if it's an isentropic process, all of that is the same. Now, if we look at that constant pressure heat addition process, the first law is going to boil down to something a little bit different. So if we apply our first law, we've got Q in minus Q out minus work in equals delta U. And I'm ignoring kinetic and potential energy changes as I typically do with these types of engines. I have a Q in and don't have a Q out, so I'm going to ignore the Q out. And it's an expansion process, so I get a work out of it. If it was a compression process, it would be a work input, but it's an expansion process, so it's a work out. And so I'm going to get rid of that work in. And now, if I just kind of bring the work out to the right-hand side of that equation, I've got delta U plus my work out, and the type of work that I have is boundary work. And remember, one of the assumptions I'm making is that all of these processes are occurring in a reversible quasi-equilibrium manner, so I can use that integral PDV equation to calculate my boundary work. And it's a constant pressure process, so that pressure comes out of the integral, and it's just P delta V plus delta U. And you may remember from Thermo 1, that is the definition of delta H, the enthalpy change. So that's it. Qn is equal to delta H, which in this case is H3 minus H2. And if we made cold air standard assumptions, we could put that delta H into terms of Cp delta T. So Cp times T3 minus T2. And of course, if you needed to calculate the boundary work, it would just be that P delta V equation that we talked about. All right, well, I hope that was helpful. We'll work some problems the next time that we meet, and thank you for watching.